Good day and welcome. I'm Jack Van Horn from the University of Virginia, and I am proud to welcome you to this edition of our 2021-2022 Foundations of Biomedical Data Science Seminar Series. This lecture series is supported by UVA's Integrated Translational Health Institute of Virginia, the UVA Brain Institute, the College of Arts and Sciences, the School of Data Science, and through a grant from the National Institutes of General Medical Sciences. This year's theme is Ethical Challenges of Artificial Intelligence in Biomedicine, where we'll enjoy presentations on Fridays from leading thinkers about the promise, opportunities, and hurdles associated with AI applications in the biomedical sciences. Our selected participants for our Biomedical Data Science Innovation Lab program will leverage these presentations as vital material for our culminating in-person grant project development workshop to be held here in historic Charlottesville, Virginia next June. Applications for the Biomedical Data Science Innovation Lab program are being accepted until January 31st, 2022. So please consider applying and or encouraging your junior colleagues to do so. We look forward to reviewing their applications. It is my honor and privilege today to welcome our speaker, Dr. Randall Moorman. He is professor of medicine, biomedical engineering, and medical physiology, as well as biological physics here at the University of Virginia. Randall Moorman was educated at the University of Mississippi and at School of Medicine and trained clinically at Duke University. He has been a cardiologist at UVA since 1990 and is the founding director of the UVa Center for Advanced Medical Analytics. Formerly, he was the chief medical officer of AMP3D, a company which provides extensible software as a service platforms for predictive analytics, processing big data from physiological monitors, health records, lab tests, and more in real time and at a glance, enabling proactive interventions, improved outcomes, and cost savings throughout a patient's entire hospital stay. AMP3D is now a Nihon Kohden company, a recent development. In continuing our 2021-2022 Biomedical Data Science Seminar Series theme, Randall's lecture today is entitled Predictive Analytics, Monitoring at the Bedside. There's been a lot of discussion these days about how artificial intelligence, big data, machine learning, and deep learning are revolutionizing healthcare by predicting clinical illnesses like sepsis. And investigators at the UVA Center for Advanced Medical Informatics have been working in this area for about 20 years. They've gained many insights. And Randall is going to share some of that work with us today, make suggestions for the next generation of researchers, and give pointers for telling what approaches are most likely to be most helpful for patients. And as always, we are streaming this lecture live and for recording via YouTube. And if you're watching on YouTube, thank you so much for joining us. Also, our specially selected 2021-2022 Biomedical Data Science Innovation Lab participants are highly encouraged to submit any questions for Dr. Moorman via the chat feature in their Zoom sessions. I'll synthesize all these questions and ask them on your behalf at the last 10 minutes or so of Dr. Moorman's lecture. And with that, welcome, Randall. We are so excited to have you, and we're looking forward to your lecture.
Well, Jack, thanks very much, and I certainly appreciate the invitation. Today, I'm going to take the opportunity to give a narrative account of the long story of our involvement in predictive analytics monitoring. I'm going to go back to how this story all started. It's not something that we revisit much in our day-to-day work, and it was fun for me to put this talk back together again after some years. A couple of important things on the title slide here. When I say on behalf of many, I'm not kidding. We've been working in this field for more than 20 years at UVA. There aren't enough slides to put down all the names of people who have made very significant contributions along the way. I'll point to a couple of names as I go through, but I won't in any way do justice to the many works of the many people that have had their hands in this. Another thing to point out, Jack has already mentioned it, is that previously I was the chief medical officer of a small company in Charlottesville that was spun up out of the licensing and ventures group that was acquired over the summer by a larger company, Nihon Kohden, which is a Japanese maker of medical monitoring devices. And I draw attention to this because, as you might guess, doing work in a vacuum or a garage can be very gratifying, but only up to a point. And to have the kind of impact on the world that you wish to have, it is imperative that you understand the commercialization process and work in that arena as well. And believe me, the nuances and challenges on the business side of the things that I'm going to be talking about are every bit as complicated and gnarly as the computers and the mathematics, and especially the clinical, the clinical issues involved. So to go back to the beginning, in the 1990s, early 1990s, I and the people that I was working with at the time thought to ourselves that this is probably a true statement, that there are detectable signatures of illness in continuous monitoring data. I think most clinicians, doctors and nurses that take care of patients would agree with that kind of statement as well. But the newness of the idea was that the detection of these signatures in real time, in real life, could change things by leading to early detection and early treatment of patients with some illnesses, and possibly to improved outcomes. And I'll point to this as being a new idea that was generated here all that time ago. This new idea, like many new ideas, went through an evolution that was first put forward by the philosopher Arthur Schopenhauer, that there's three stages. First, a new idea or a new truth is ridiculed. Second, it is violently opposed. And third, it is accepted as being self-evident. And this kind of cynical point of view of the world, in fact, turns out to be almost exactly correct. But we've been gratified to see that we've made it all the way through. And now everybody generally agrees with this idea that early detection of signatures of illness might be a good thing. Didn't used to be that way. In any event, we began this story back in the 1990s working on the problem of neonatal sepsis, that is to say, bloodstream bacterial infection in premature infants in the neonatal ICU. And to say that the diagnosis of this illness is difficult is a massive understatement. So if I asked you, is this baby septic? Your question in return might be, what baby? So it turns out that under this covered crib, there does indeed lie a baby weighing a couple of pounds, maybe 3 pounds. Very hard to understand from looking at that patient, even when you get up close and personal, as to whether that infant is having symptoms of illness or signs of illness. But sepsis is a bad thing with potentially catastrophic consequences. And so doctors and nurses are forever wondering about whether their patients are septic and then doing tests. Now, a blood draw in an adult is no big deal, but to draw 2 or 3 cc's of blood from an infant whose circulating blood volume is 70 or 80 cc's, especially if you want to draw more than one test, well, that's a major consideration about whether or not to do any tests or not. And as a result of the suspicion of this bacterial illness, antibiotics are given a lot to infants. At any moment in our NICU through the years, about a third of infants at any moment are receiving antibiotics because of suspected or proven sepsis. So a dire problem, difficult to diagnose. Is there a signature of illness? Well, in 1959, I found a paper from 1959 that pointed in one direction: changes in heart size in the dyspneic newborn baby. Well, it isn't the heart size that was interesting in this paper. It was observations about the heart rate. So he talks here about the speed of the heart rate, but then he makes this statement right here. A characteristic finding at the height of respiratory distress and within a few hours of the onset of the illness was a fixed rate between 110 and 120 beats a minute that did not vary if the baby cried or was roused to physical activity. There follows some nonsense about heart sounds, but then we get down to the bottom here. When they survived, early signs of improvement were a rise in the heart rate, that's fine, or a lability of the rate as shown by variations in it with exertion. So this was a big clue that the pattern of the heart rates might hold information. At the time that we started with this work, there was a decade or so of research into heart rate variability in adults with heart disease. So this seemed like a likely place to go looking. So sure enough, after we figured out how to make measurements, we made long recordings of EKGs and determined heart rates from infants in the neonatal ICU. And what I'm showing you here is not a plot of heart rate, but a plot of the times in between heartbeats. And so this is upside down heart rate. Slow rates up here, 500 milliseconds in between beats is a heart rate of 120 beats per minute. Fast heart rates down here, 300 milliseconds per heartbeat is a heart rate of 200. But there was, no matter how you plot it, there's a very striking difference between an infant at the height of his or her illness and after successful recovery. Yes, there was a bit of a difference in the heart rate, but it is the variation of that heart rate that is very strikingly different. Now, it doesn't take a lot of statistical or mathematical prowess to be able to tell that time series from that time series, and we worked a lot on that, but just to put some things in context, here's our paper from 1994, and here we're showing a neural network based on polynomial nodes to distinguish the heart rate patterns of the sick baby from the heart rate patterns of the well baby. So, neural networks have been around longer than our work, but as new as all those techniques might appear to you to be, in point of fact, they're pretty well founded and have been around for a long time. So the upshot of this was that this particular technique and other techniques as well did a very robust job of distinguishing babies early in the course of their illness, day one, from after recovery over here. And so we crystallized our new idea a little bit better down here at the bottom. The new idea is that the signatures of illness with respect to neonatal sepsis, low heart rate variability. And so we set out to find out more about that. And we fashioned tools to make long recordings and actually look at the EKG signal. Here are a few heartbeats from an infant up here, and then rather longer time series of the time in between heartbeats here. And we knew what was happening with the infants, and so we could match what we knew clinically with what our eye told us about the patterns here. So this is what normal neonatal heart rate variability looks like over about a 25-minute stretch of time. And EKG aficionados will note that this is sinus rhythm, which is essentially the only heart rhythm that the newborn infants have. They aren't really plagued by cardiac arrhythmias. Okay, so here's an infant who was several hours before the clinical diagnosis of sepsis. That is to say, baby, for all intents and purposes, was clinically fine, but a few hours from now is going to be diagnosed with that dire illness. And so what about our new idea about reduced heart rate variability? Well, okay, well, sure enough, through here's a stretch of 10 minutes or something of heart rate variability that's certainly lower than what I just showed you a second ago. But lo and behold, here are these other things. Now, this is still the time between heartbeats. So from time to time, there's some long intervals. That is to say that the heart slows down some during these times. And this is a very striking looking thing to look at, a flat line with spikes going up in it. This is to say that the rhythm remains sinus rhythm, that is to say normal rhythm. Here we are, same baby a little bit later. And now this is very strikingly different from normal. And yes, if you can find a quiet baseline, the variability is very much different than what I showed you before. But here are deceleration after deceleration after deceleration. Now the bradycardia alarm is at about the top of the screen. So I'm showing you some very pronounced examples, ones that would have in fact triggered the alarm at the bedside, but that's not always the case. And here are some perfectly good decelerations over here that got nowhere near the alarm threshold. And there were many, many of these as well in what we looked at. Those of you interested in cardiac electrophysiology, what's happening is these are sinus pauses. There's no evidence for overt sinus exit block. There's no evidence for AV nodal slowing. The mechanism of this, as much as I like to think I know about this kind of thing, is not totally known to me, but the phenomenology is blindingly clear here. Now, we set out to get mathematical measures to distinguish these things. I'm sorry, here's another example. May have been this example, in fact. So heart rate variability a week before the diagnosis of sepsis. This is about a 25-minute record here. A few hours before, here the bradycardia alarm would be way up here. And then as before, the perfectly storming appearance of heart rate decelerations against this backdrop of reduced variability. So our methods for quantifying this were centered around the idea that the histograms of the heartbeat intervals would look different between the normal and abnormal episodes. And so if you conceive of a normal record, here is one, as being composed of many small accelerations, this again is time between heartbeats, along with many small decelerations, then the histogram turns out to be, if not exactly Gaussian, at least certainly bell-shaped with representations on both sides of the median. So looked at in this way, the abnormal record presents itself as a very abnormal looking histogram. So here are the decelerations here. And so now there's a fat tail on this part of the histogram. And I hadn't drawn attention to it previously, but the accelerations have all been clipped off. And so the half of the histogram that reflects accelerations is truncated on that side. Now, some of you may have been reflecting upon the fact that this heart rate pattern, reduced variability and decelerations, is precisely the pattern that clinicians that are delivering babies in the labor and delivery suite are looking for in the heart rate patterns of the fetus. And this idea, reduced variability with decelerations, is a mantra up there that it's time to do an emergency cesarean section. That is a time-honored practice. 100% of fetuses are monitored in that way in the bigger hospitals. Certainly it's true at our hospital. And cesarean sections the decisions are made based on picking up strips of paper from the floor, eyeballing it, looking for this pattern, and then saying go. So it shouldn't be surprising that a premature infant who by rights should still have been a fetus inside a uterus should show distress with the same kind of heart rate patterns. Now, as part of working on this, we got involved with the idea of measuring entropy in these heart rate time series. This is too long a story to go into now, but suffice it to say that entropy in this domain, from the nonlinear dynamical domain, which is where we borrowed the concept, is a matter of looking for repeating patterns. And so in short, as we examine this time series, we look for patterns that repeat themselves tolerably well. And let's just say that we're interested in this pair of green points, and as we scan everywhere else, we find a tolerably similar other pair of green points. And now the question is, does the point that follows, the red point, also match from the original over into here? And the more that is true, that is to say, the more truth there is to the idea that patterns repeat themselves, suggests that the system is of low entropy in the sense that it's not generating new information as it goes along. Now, after that, there are some details about how you count things and how you calculate things. And we found some difficulties with a current measurement, and we developed our own that we called sample entropy, and that went on to become something unto itself, but is a good example of the kind of time series mathematics that we have used. So through the years, we have kept ourselves busy with adapting and optimizing and developing new to the area mathematical time series measures. And this is a sort of a narrative account of some number of them. And I'll be coming back to the last one, the most recent one, in a little bit. Sample entropy went on to become a kind of a one-stop shop for chaos theory in all fields at all times, and has gathered some popularity. Okay. So the way that we put together our mathematical measures was using logistic regression. And I'm sure you're familiar with that from the modern discussions of machine learning and deep learning. And to do this, you need a set of data from infants that aren't sick. You need another set of data from infants are, or at the time that they are. You label one set of data as outcome equals 0. You label the other outcome as outcome equals 1. And then you model the log odds of the event as a straight line, as a coefficients times variables plus an intercept. And you end up, by the time you back out the probability, with this familiar expression here, where you have exponentiated versions of a linear combination of variables. And those of you that remember y equals mx plus b, well, that's exactly what this is. Here is the intercept. Here is the slope, here is the variable. It's multivariable, so you can put more of these things in there. And when all was said and done, we based our index on 4 measures that we got from the time series. The standard deviation, because sometimes the long records were quiet throughout. 2 measures from the histogram, the acceleration-based measure and the deceleration-based measure, and this entropy thing that I've been telling you about. So we fit our logistic regression model with all of our data and came out with a measure that we could show clinicians that reflected to them the probability of sepsis in the next 24 hours. Now, rather than give the clinicians a probability as such, we gave them the fold increase in the probability of the event with respect to average. Thus, a normal infant hanging out in the neonatal ICU should have a score of 1 or less, average risk or lower than average risk. An advantage to using this unit of measurements, which we have stuck with ever since, is that it makes for English language discussions about what the measure means. So if I tell you that this score is 2, that means your infant is twice as likely as average to have an event, and clinicians can resonate with this kind of thinking. So I'm showing you here 14-day records from 2 of the infants. This is from a paper in 2003. We're up to there now. Showing you every 6-hour measurements of this score in infants on their way to having the diagnosis of sepsis. And the diagnosis of sepsis on this timeline is denoted by this acronym CRASH, which stands for cultures, resuscitation, and antibiotics started here. And what you can see from this is in both of these cases that we selected, there were waves of increase of this score over the days and days prior, but there was certainly evidence for increased risk prior to events. Now, this score doesn't happen in a vacuum. There are a lot of other things happening to that infant in the way of being on ventilatory support or having central lines, drugs, other measurements that people are making, laboratory tests, and so forth. And so my colleague, Doug Lake, with whom I worked closely since 2001 or 2, started making these things that we have called event maps that place on one visualization the presence and the severity of abnormality of events and measurements during the hospital stay, and superimposed is this score here. We call it the HRC index. It's also called the HERO score. But here it sits, and here are its units over to the side. And this is a very typical looking one where blood cultures were drawn here, antibiotics were given here, the diagnosis of sepsis was made here. Other things were going on in the way of tachycardia and temperature instability and whatnot. And here's a gratifying rise in the HERO score prior to the clinical diagnosis. And this is the spirit of the use of predictive analytics monitoring at the bedside. If a patient has a low risk that rises, then it makes sense to us for clinicians to go see that patient and evaluate that patient in the light of there is possibly a subacute, potentially catastrophic illness on its way. So about this time, we applied for and were issued a patent for this idea of early diagnosis of subacute, potentially catastrophic illness. And I draw attention to this simply because it is the first step along the commercialization pathway. No company will undertake to manufacture and distribute something that is in the public domain. I'm sorry that's true. I didn't invent that, but that is the hard truth of the matter. And so the commercial product that came out is this, which is the HERO monitor. It is run continuously in the the UVA neonatal ICU since the spring of 2000 and since the fall of 2003 when it got its first FDA 510K clearance. And this is the spirit of it. Here is a low score. It's less than 1. Here it has gone up. At this vertical yellow line, here are the 30 minutes of heart rate that were present at that time. Here is reduced variability. Here are decelerations. It is a very robust and repeatable and repeating signature of illness in that population. And since we're talking about history, that this is the first, so far as I know, premature infant who was diagnosed with sepsis without having any clinical illness to go along with it. So this was within the first week or two of putting the HERO monitor up in the UVA NICU. Here we are over 10 days, and here goes the score, nicely less than 1 until it wasn't, and it rose to a value of something over 2. Here are the heart rate records that go with it. Here we are a week prior, let's call that normal. Here we are at the time of interest, reduced variability, decelerations, no great change in the heart rate. And then here we are after the fact, back to normal again. So what happened was that the clinicians taking care of this infant knew the story, looked up on the wall, saw an increase in the HERO score, and undertook to evaluate the patient for sepsis. So they looked at the baby, no clinical signs of illness. They drew the usual suspect laboratories. All of them were normal, except for one. They sent a sample of blood to the microbiology lab and asked for it to be cultured. And sure enough, 12 hours later, they received a call to say that the blood was growing a gram-negative organism, Serratia marcescens. Now, the death rate in the NICU from Serratia sepsis is on the order of 40%. 4 out of 10 infants with this diagnosis die as a result of it. In this case, they got the blood culture result back. They could not ignore it. They started antibiotics, HERO score came down, and the baby not only didn't die, the baby never got sick. Now, that is a remarkable event. An infant who contracts an acute infectious systemic illness where the death rate is 4 out of 10, but it is diagnosed at a time so early that they have not become ill and further receives appropriate therapy on the spot, the entire illness was averted. That is a wonderful story. It has galvanized all of us that work in this field. I got chills when they called me from the NICU and told me about it. I get chills telling it to you today. It is a remarkable realization of the potential of what we can do with data from patients to improve outcomes. Now, what I've just told you is a great story, but let me go ahead to say that we looked at more patients that had this kind of event. That is to say, a large abrupt increase in the HRC index or HERO score. And what we found was that fully half of them had an infection that required treatment. So this is the positive predictive value. It's 50%. If you haven't dealt with positive predictive values for rare events, let me tell you, that's a big number. In contrast, the positive predictive value from my clinical world of a treadmill test where everything goes wrong with the patient that possibly could go wrong, the positive predictive value of that finding for a heart attack in the next year is about 10%. So this positive predictive value of 48% is a very big number indeed. Other infants that had this finding had other kinds of illnesses, and we were reassured from this that was not a one-time occurrence. So to further hammer home the question or answer the question of whether this is going to help others, we undertook a randomized clinical trial. So this became, by the time it was over, the largest randomized trial ever undertaken in premature infants. I beg your pardon, for this or any other reason, 3,000 infants of less than 1,500 grams birth weight were randomized in 9 neonatal ICUs up and down the East Coast. And the randomization was extremely simple. Once the infant got there and the parents signed consent, we either assigned them to have this risk shown to clinicians or to receive only standard of care and not have it displayed. There were no mandated interventions. No one had to look at the monitor, let alone report on it, let alone act on it. There were 3,000 infants, more than 100 doctors, more than 1,000 nurses. The primary outcome measure had to do remains a popular sepsis-related outcome, and we had other outcome measures, in particular in-hospital mortality. Now, the big result from this trial was in one of the other outcome measures, and that was that there was decreased mortality, that is to say, improved survival when we showed the risk display to clinicians. These are survival curves over the 120 days after randomization that the trial was designed to inspect. Here is the survival of infants receiving conventional monitoring. Their mortality, beg your pardon, their mortality over 120 days was a little more than 10%, which is exactly as expected from US national statistics. The mortality for the infants who had the new monitoring was 8 and a bit percent, a relative reduction of something more than 20%. So 20% improved survival from turning on a computer screen and showing it to the people taking care of the baby. I'm not going to show you the results, but we went on to show that the survival benefit was very heavily concentrated in the infants who got septic, where the mortality rate fell from 20% with conventional monitoring by almost half to 12% in the infants that had the predictive monitoring as well. So this is a wonderful result. The paper was published 10 years ago. As far as I know, it remains the largest randomized trial of this kind. It will be superseded next year when we complete a similar trial that's currently going on in our cardiology ward. Okay, so that was a flagship finding in the field and has galvanized, as I say, us to continue to do other work. And I'm going to give you some examples of that kind of thing as well, but I'll return at the end to the infants again. Okay, so this is logistic regression. We have used other kinds of machine learning. We are dabbling our toe into deep learning at this point. But one interesting finding that's representative, I think, of the kinds of findings that an exploration of different kinds of machine learning will bring out is how different statistical models view important variables in the clinical population. So this is a small segment of a bunch of results from a similar study, not a randomized trial, but a study that we did in the pediatric ICU, where the range of age goes from 0 to 18 years. And we were interested again in the question of sepsis, and again we use predictive models. So what I'm showing you here is how the methodology can lead to differences in the way that the variables are treated or looked at in the overall statistical model. Now, so here is this is the plot of the log of the odds as a function of the age of the patient in the pediatric ICU. Down in the footnotes, we're using restricted cubic splines to get away from the fact that this would have to be a monotonic straight line. And this is the story here, okay? And this is the analytical result that comes back from the fitted model. But over here, we used a random forest model, and we were struck by the difference in how age was treated when you could look at it in this much more granular kind of way using random forest methodology. And it resonated clinically with the doctors up there, that they felt that this represented better what they thought about, and that is that infants in closer to the neonatal period had the highest risk in their unit, not the finding after you do the cubic spline kind of approach, but very much the finding over here if you let the data drive the model. Now, As I've said, we have moved on beyond the NICU, and in point of fact, we have found that there are signatures of illness everywhere. I'm showing you results here from a few years ago in a large study that we conducted in our surgical ICU and our medical ICU, and we threw in NICU results over here as well. But this was to establish the idea that the signatures of different illnesses might differ from each other. And so here I'm showing you what I'm calling a signature of illness, and I'm going to draw attention to two of the colored tiles to explain what I'm talking about. Each of these is a plot of the log odds as a function of the measured variable, and they all come from multivariable logistic regression models. And these log odds plots are from the multivariable model. That is to say, these are the associated odds of the illness given all of the other variables are in the model at the same time. And the way to interpret these kinds of plots are, for example, this one, which I've brought over and expanded over here. This is to say that the odds of emergency intubation in the surgical ICU go up as the mean respiratory rate goes up. Patients that are breathing faster are at higher risk of requiring emergency intubation. Not a stunning effect, but that is the truth of the matter. So this is colored orange because the risk increases as the measured variable increases, and it's deeply hued because the p-value was very low. Here's the counter example. We're now talking about bleeding, also in the surgical ICU, and we're looking at the diastolic blood pressure. This is blown up over here. As the diastolic blood pressure is lower, the risk of the event goes up. Bleeding leads to low blood pressure. We all knew that coming in, not a surprise, but these are what I mean when you put them together by signatures of illness. And the way you analyze this is you go stand across the room, you look at the respiratory models, and you say to yourself, yes, those look pretty similar from one adult ICU to the next. And then you stand across the room and you look at the hemorrhage models and you say, yes, they look pretty similar from one adult ICU to the next. But wait a minute. So here's sepsis now in adults. The signatures of illness do not look like each other. They look different. In point of fact, in the medical ICU, sepsis presents more like hemorrhage. In the surgical ICU, sepsis presents more like lung failure. Here's the neonatal ICU. All of the signatures look the same diagnoses, but now they all look exactly like each other, and none of them look anything like what happens to adults. So this is to make the point that illnesses in populations, in hospital settings, have signatures that can differ from place to place. It's a strong argument against using a single predictive model everywhere. And so when we go to introduce predictive monitoring somewhere, every unit has its own models. Every target illness has its own as well. So I'm going to take you now to, I'm sorry, now just one moment. I'm going to take you now to what we are currently doing in the ICUs about displaying risk to clinicians about patients. What you're looking at here is a COMET monitor. 35% of beds at the University of Virginia Hospital have real-time predictive monitoring. Some of those are the NICU, and I've already shown you that. The rest of them have this thing that we call, as I say, we call the COMET plot. And I'm showing you now results from old de-identified data, real patients. I have no idea who, and I actually have no idea when these data were collected either. So for this unit, we elected to show the clinicians the risk of sepsis, again, fold increase, 1, 2, 3, 4, 5, and also in-hospital mortality. And so what we're showing you is every bed in the PICU, the bed number is shown in the head of this structure. We call them comets because they look like comets. The tail of the comet is 3 hours long. So if you were an attending physician in the pediatric ICU and you walked in and saw this, one use case is that you don't stop walking and you just direct your feet to beds 91C, 92, or 96 to see what is going on in there. You don't go in there armed with a diagnosis or a medication or a plan. Your attention is drawn to those because they are at high risk and in some cases increasing risk. The system is set up in such a way that you can isolate a single patient and look back over time to see, is this a new problem or a chronic problem, or just exactly how long has all of this been going on. And as I say, we have this available for a lot of units inside the hospital. And this is our current incarnation, current application for how we show clinicians what is going on with their patients based on the data that are streaming in. Now, these estimates are based not only on the EKG time series that I showed you before, but actually everything that comes from the bedside monitor, which includes O2 saturations, blood pressures, our arterial waveforms if they're present. And in addition, we also use everything that's in the EHR, laboratory tests and vital signs. Most systems of this kind restrict themselves to what's in the EHR. There's some theoretical problems with that, but we use them too. And we add, like I say, the real-time continuous aspect to it as well. So let me go back to sharing here. Oh, I'm sorry, I beg your pardon. That's not what I wanted. Let me go back to presenting here. Okay, so in our surgical ICU, which is where we put the first of these displays in 2015, we counted heads in the 6 months before and the 6 months after turning it on. And we were interested in outcomes there, not a randomized trial, but was there an impact of outcomes? And the major result was that the rate of septic shock, so this is sepsis plus severe hypotension, fell by half after we turned on the display. In the medical ICU nearby, where there was no display, the incidence of septic shock remained much the same. There were some improvements in some other outcomes. It was a fairly large study, but this was the only one to reach statistical significance. It remains statistically significant after taking age and illness severity into account as well. So good justification for further randomized trials, such as the one that I mentioned earlier. Now I'm coming back, let me come back to and finish with an observation about where all of this started. This is recent work and of very high personal interest. So all those years ago, we based it everything that has happened subsequently started when we looked at this and said, this is a signature of sepsis in premature infants. And now, this is not a question we asked ourselves back then, and I'm glad we didn't, but looking back, it's interesting to think about, how did we know that that was true? And now, here's a modern question. Having asked that question, how do you even begin to figure out whether you knew you were right or not? Okay, so enter a technique called highly comparative time series analysis. So in 2013, Doug Lake, whom I should have mentioned before, reviewed a paper with that title, and for the next several years was telling me what a good idea this was. And after a number of those years, it finally sunk in what he was talking about, and we set forth together to try with others to try to figure something out. Highly comparative time series analysis. What is involved is, or what it was in this paper, was the investigators took several thousand time series from all sorts of origins that they were able to find: geology, medicine, astrology, anything that they could find, large time series, and then did numerical calculations on them. They call them operations, using a very large number, thousands in fact, of different kinds of mathematical operations. And when they come out of it, they have millions of results. And they've used here RNA array RNA arrays to visualize the kinds of results. So this is a massively comprehensive characterization of time series on a scale that it took me a long time to understand what they were even talking about. But with Doug and with Tim Clark, who in the School of Data Science and School of Public Health, we managed to get this done. So here are the families of mathematical operations, a description and some examples. And we had, amongst all of these things, 2,500 numerical algorithms that we could apply to time series. We applied them to two sets of time series. The heart rate and the oxygen saturation in each time series was 300 points long. So this is a massive, simply massive amount of computation. So I'm leaving out some of the intermediary results to take you to the result that was most directly relevant to the point that I brought up. So here is a Zoom call from a year ago. And on the call are myself, Karen Fairchild, who's a clinical neonatologist and the engine for neonatology research in our group over the past 5 years and more. Justin Nistroy, a former math major at the University of Virginia, and also master's degree in data science from the University of Virginia, at the time working in the group of Tim Clark, Tim drinking. That doesn't happen often, but there he is drinking. And here is Doug Lake here. And the result here is not so consequential, but it gives me a chance to say what we did. So out of all those algorithms, we were able to determine those that were the best at characterizing neonatal heart rate and oxygen saturation time series. That is to say, we used an unsupervised clustering technique and derived from it 24 measures that as I say, covered the waterfront for characterizing the dynamics and the distributions of heart rate on one hand and oxygen saturation on the other hand, time series. So we're now armed with a way to look at all possible patterns of neonatal heart rate. So what we did was we took those 24 descriptors of neonatal heart rate dynamics and prepared a logistic regression model on the patients that were septic. And then we inspected the results with regard to what records did this new approach think were associated with the highest risk of sepsis in the next 24 hours. And lo and behold, here they are. These are 300-point heart rate time series records discovered using an unsupervised clustering method, and then the results of that in a logistic regression model on sepsis. And look what we have: reduced variability and decelerations. These are the top 16 riskiest records out of a very, very large data set. Here we have Doug drinking, and Karen, I didn't know she was doing this, but that was the first time I saw this, and it hit me like a ton of bricks that this was the answer to the question, how did we know we were on the right track? I don't know, but I am assured of that by this very comprehensive mathematical analysis coming up with exactly the same result. So this is a figure that I made when the model predicting sepsis using results of an unsupervised clustering technique predicted highest risk, reduced variability, decelerations. When the model predicted lowest risk, high variability, accelerations, and then these two records are at about the 50th percentile and the 75th percentile or something like that. They are of diminishing risk as we move across like that. Now, there ends the most of what I want to say about what we used to call statistical pattern recognition, what we now call machine learning, big data, artificial intelligence, all the other things that you know about. Let me say that in this field, the new frontier is understanding what to do with this information. And so I've listed a to-do list of things that begins with framing the clinical questions that are of importance to doctors and nurses, and ending with figuring out how to get it distributed. And I will tell you, every step along that pathway, we have stumbled, fallen, sometimes picked ourselves up, sometimes not. But this is what is required to get from point A to point Z in this field. I'm ending with this picture, which is a photograph that I took more than 10 years ago of our group at work. And it's to make the point that this is not a job for some person in isolation, that this requires a multidisciplinary team of people working on it. And this is obviously not rehearsed or posed or staged or any of those things, but just to point out some people. This is John Catwinkle, for many years, the director of neonatology here, and a world eminence in that field. Karen Fairchild, I've already pointed out before. Ho-Shik Lee is a PhD physicist, was the postdoctoral fellow of John DeLoss, distinguished professor of physics at William and Mary. Matthew Clark at the time was a postdoctoral fellow. He was then the chief science officer at AMPT, and he's now a principal engineer at Nihon Kohden. Brooke Vergalis is a clinical neonatologist, as is Rob Sinkin. Not shown in this picture is Doug Lake, but there's very much this picture, very much this idea of a committed collaborative group of clinical doctors and quantitative scientists or data scientists come together to communicate across a wide gap to address a problem that's of importance to patients and their families and the people that take care of them at the bedside. With that, I'll stop talking. I'd be delighted to answer questions, and thanks again for the invitation.
Randall, thank you so much for what an engaging talk. That was really wonderful. And I love that you've ended on this notion of team science. It really does take a village, especially when it's a very practical problem that you're trying to address. And even in those cases where it's a practical problem, is that these things aren't simple, and you need experts from a number of different domains to be able to address them. I have a couple of questions for us to get you kind of started. You mentioned that a lot of this work comes from devices that sit at the bedside of various patients. And I'm kind of curious, have you explored like putting this onto, say, taking it away from the bedside and into the community, for example, like on a smartwatch? Could something like this be something that somebody could have running on their iPhone watch and, be sound an alarm should somebody's heart rate descend into some degree of, the wrong end of the entropy spectrum, if you know what I mean?
Well, so there's several interesting pieces of that, and many of which we have not touched on. I consider the ambulatory monitoring problem to be every bit as big or bigger than the hospital inpatient problem. Recall that I pointed out as we went by that the positive predictive value, that is to say, the probability that an alarm is a true alarm, inevitably falls as the rarity of the event increases. Mm-hmm. And so if you're out there monitoring everyone for things that don't happen very often, the very, very great majority of alarms are going to be false alarms. Now, this is being tested out there because there are atrial fibrillation detection algorithms built into Apple Watches now. And there are other ways, other kinds of things as well. And atrial fibrillation, very important clinical diagnosis, calls for intensive treatments. And I'm very interested to see how all of that is going to work out. I must say, I don't have any personal interest in going after that market because of, I think, the false alarm difficulty is going to be very high. So the other aspect of this that I wanted to comment on is the whole idea of alarms in the first place. So if you know that alarms are going to be false, I wouldn't issue them. The inpatient story is very much attuned to the idea that you're looking for changes in risk. People come in sick, they should get better. people get better, they should stay better, they shouldn't get sick again. And so the whole thinking of the clinical team is very much, are they okay? Are they okay? Are they okay? In the NICU, it's, are they septic? Are they septic? Are they septic?
Right.
So the idea that you've got something in real time, or it refreshes every 15 minutes or an hour or whatever, but anyway, in reasonable real time, that's keeping you abreast of current events and somebody that you know an awful lot about, that resonates strongly with me as a clinician as a useful thing to do, much more so than the ambulatory one.
You mentioned afibrillation, and one of the big risks with people who are in AFib is an increased risk of stroke. And I'm curious if you mentioned iWatches have this capability in them now. I'm curious if you've attempted to apply this to looking at AFib patients and their risk of stroke, for example, in contrast to sepsis in neonates. AFib predicting stroke in cardiac patients, for example.
Well, there are steps in that direction have been toward improved identification of atrial fibrillation from inpatient data, from the inpatient EKG telemetry. So we did this work a few years ago. We applied our time series interests towards this. It's not the hardest thing in the world to diagnose, and it's foiled by a few things like premature beats, but we worked hard on this and developed what I think is a very nice algorithm for detection of atrial fibrillation given an EKG recording. So we went back in our records and found that there was a lot of undiagnosed atrial fibrillation in our intensive care units. In fact, about half of the atrial fibrillation that occurred in the ICU in patients that didn't have it when they walked in and weren't already, on the radar. But about half of the new atrial fibrillation in the ICUs was not commented on or acted upon by clinicians. And so to the end of detecting atrial fibrillation so as to start earlier diagnosis and therapy, that is a great idea. Our bandwidth is not extended clinically to be able to do something about that, although I think that picture may be changing soon. With regard to detection of the risk of stroke, we've not taken that additional step. We're at the find the atrial fibrillation part. Later would come in larger studies. To what extent was atrial fibrillation related to stroke? The real question, and I think this actually got addressed, I think recently, is if you do all of that and then randomize patients to blood thinners, which is of course the stroke prevention step that you take, if you give them ambulatory atrial fibrillation detection devices, and when atrial fibrillation is diagnosed, randomize them to blood thinner or no, is there an impact on the stroke rate? There's a recent study that had a negative result and said the stroke rate was the same. I don't know everything I need to know about that, but that at least is the ultimate design, or that is the design of the study to answer the ultimate question that you just, the way that you've brought it up.
What do you think some of the current or kind of like just more immediate challenges exist? What are some longer term challenges that need to be overcome, and where can data science continue to play a role?
Two things. So my advice to the young data scientist is go find a young clinician who is obsessed with a clinical problem for which early detection might lead to therapies that can improve outcomes, and you will be codependent. Clinicians are too busy to go do all of the programming required. Programmers do not have their hands around the nuances and complexities of clinical medicine. I'll say with specific regard to machine learning models in healthcare, I have a lot of questions these days, and I mentioned this going through, about relying only on the electronic health record as a source of data. And the reason for that is that it very much reflects, in addition to the patient and the illness, it very much reflects the clinician and the health system and the decisions that they make, the diagnoses that they're entertaining, and the policies of the hospital. So imagine that what a patient it is admitted to the hospital with shortness of breath and an abnormal chest X-ray. One clinician might very reasonably think, well, this is decompensated heart failure, and order blood tests and medications that relate to that. Another clinician might also reasonably make the diagnosis of pneumonia and go off on a completely different tack. Now, the data that those clinicians gather will be very different from one from the other because of their diagnosis or their working diagnosis. And so they'll be investigating different aspects of the patient. And the idea that you have colorized the patient and filled in all the dots on the invisible man so that you can now make out that form distinctly is just not right. It doesn't work that way. And so I worry about approaches that use only EHR because of incompleteness, inaccuracy, and this is supposed to be about ethical and equitable AI. Believe me, there are issues about the way patients get worked up in hospitals based on their race and ethnicity, and that will inevitably play into the data sets that you have to analyze.
That brings me to kind of a final question is, are there communities in the US or internationally where a technology like this might be really helpful for addressing things like, for example, infant mortality rates?
Well, I think that a harder question would be, is there a hospital in the US that doesn't need to figure out some way to use all the data that they've got on their patients?
Absolutely.
Individualized predictions. Again, would that change the infant mortality rate of the US? I don't know how to answer that. Would it change the mortality rate of premature infants in neonatal ICUs in the US? Without question, there's a large randomized trial that says exactly that.
That's fantastic. Well, with that, Randall, thank you so much. We really appreciate you sharing with us this important work that you're doing and have been doing, and the work of your team. You are a good representative of all their efforts. And thank you so much for contributing to our seminar series. Everyone, thank you so much for taking part, and everyone have a great weekend, and we'll look forward to seeing you